So notice that in this diagram, we have points in which the ammeter and the ohmmeter are connected to the resistor. Those points we call nodes. So at this point in which the ammeter and the ohmmeter is connected to the resistor is one node. And at this point, that's another node. So simply, a node in a circuit is a point in the circuit where two or more components are connected. Now, a branch in a circuit, which is also called a junction, is a point in the circuit where three or more components are connected. So in other words, if it's like a branch of a tree, a fork in the road. So if we look at the ammeter on the left in the circuit above, let's look at that. So we have the ammeter. If the ammeter were just attached to the resistor, we would see that it was attached at this node. But as soon as we place that third component, that ohm meter, we have a fork in the road. We have a branch in our circuit. So this collection of wires, indicating three components here, corresponds to our branch. We can also call this our junction as well, and we'll use those phrases interchangeably. The thing about current, when it's passing through a branch, it can separate into different amounts, simultaneously taking each path away from the branch. So in looking at this, before we attach the ohm meter, the current was going straight through that node, leaving the ammeter, entering the resistor. But as soon as we put that third component, the current is able to branch, able to take two different paths. Because it's able to take two different paths, the amount of current on either path may be different. So the current in the lower path through the resistor may be different than the current through the upper path through the ohm meter. The thing to be aware of is that the current into a node must equal to the current out of a node. So in this situation, if we have a current I entering this node, then that's going to be equal to the current I1 plus the current I2 leaving the node. So the total current in must be equal to the total current out. So I in equals I out. And in the case of our ammeter, ohm meter, and resistor, the ammeter then is measuring the total current through the combination of the ohm meter and the resistor. Let's talk about different ways in which we could wire a circuit. And specifically, different ways in which we could attach two or more components. Beginning with a series connection. Two components are connected in series when electric charges have only one path between them. So for example, when we had our ammeter resistor combination, this combination is a combination in which these two components are wired in series. One occurs right after the other. There is a single node where those 2 points are attached. Well, it doesn't have to be a single node. I guess what I mean by that is there are no branches in the connection between the ammeter and the ohm meter, between these two components. So what that means is there is one and only one path for current to move through these two components. And that single path means that these two components are connected in series. Now, a series connection exists when the two components are connected end to end. And as we said, providing a single path for electric current. That single path means that each component has the same current passing through it. Another type of connection is a parallel connection. Two or more components are in parallel whenever they are connected at two different points on either side of each component. Well, we often draw that, or I'll often draw that as the components, I just align them in parallel like I have in the diagram on the left. Let's return to our ammeter and resistor combination. So we have this ammeter attached to this resistor, but now let's add that third component, that ohm meter that we've talked about before. So notice how the ohm meter is attached. The ohm meter shares 2 points in common with the resistor. And notice how those 2 points are on opposite ends of each component of the resistor and the ohm meter. So in this diagram, the ohm meter and the resistor are connected in parallel. But notice, the ammeter is no longer in series with the resistor. And the reason why the ammeter is no longer in series with the resistor, it's because now there is more than one path for current to move between the ammeter and the resistor. So we can't say they are in series anymore. What we can say, though, is that the ammeter is in series with the combination of the ohm meter and the resistor. Because that combination, notice, if let's go ahead and replace that combination with maybe a single representative diagram. So I'm going to move this up a little bit, and I am going to replace that ohm meter resistor combination just with a single component, and I'll just indicate this is a omega R, representing our combination of ohm meter and ammeter. And this combination, the ammeter is in series with, because there is a single point in which the current moves through the ammeter, leaving the ammeter, entering the ohm meter resistor combination, and leaving the ohm meter resistor combination. So in this situation, in this diagram, we see that the ammeter is in series with the combination of the resistor and the ohm meter. But if we go back to our previous diagram, we see that the ohm meter is in parallel with the resistor. So what does that mean? What does this all mean? Well, we said that the current into a device is equal to the current out of the device. So let's look at the current going through the ammeter, and let's call that I sub A for the current through the ammeter. And let's look at the current through the resistor, which I'll call I sub R, and let's look at the current through the ohm meter, which I'll call I sub omega. Well, the current into that point, into that node, I sub A, must be equal to the current out of that node, I sub A. And the current through the ohm meter resistor combination, I sub A, must be equal to the current leaving the ohm meter resistor combination, I sub A. So in other words, I sub A, the current through the ammeter, must be equal to the current entering that node plus the current leaving the node, the combination of the current of the resistor and the current of the ohm meter. Now in the circuit that we drew previously, notice this connection here. Let's add some nodes. So I'll add a point in between the battery and the ammeter on the left. And I'll add a point between the battery and the ammeter on the right. So looking at these points, if we were to look at the current in this circuit, the current, I like to draw it coming from the battery, though the current exists everywhere in this circuit. Well, we could see that since current has a single path between the ammeter and the battery, the ammeter on the left is in series with the battery. And then that current branches between going through the resistor and going through the ohm meter. That current recombines at the branch / node on the right and returns to being the current through the ammeter on the right, which has to be equal to the current through the ammeter on the left. And notice that ammeter has a single point of attachment with the battery. So the ammeter on the right is in series with the battery. The ammeter on the left is in series with the battery. The ohm meter is in parallel with the resistor, but the combination of the ohm meter and the resistor is in series with both ammeters. So we could represent that as, here's our battery, here's the ammeter on the left, here is the combination of the ohm meter and the resistor. This will be our equivalent component. Here's the ammeter on the right. And notice each of these components or collection of components are in series.